Okay, so here we go. This is the derivation of the wave equation. And I'm going to show you two different derivations, and then I'll show you one simple solution to the wave equation. So this is the wave equation. Let me go ahead and start my little animation here. Does that start? There it goes. So this is a slow motion wave on a bead. So I live in Louisiana. We have Mardi Gras beads all over the place. So this is a wave in a string of beads. And so the wave equation gives you a relation. This is a one-dimensional wire. It gives you a relationship between the change in position this way and the change in position this way. So it's a second order partial differential equation that depends on both time and position for the displacement y. And it's kind of an important equation. It shows up in a lot of places. Of course, it shows up in waves. It shows up in electromagnetic waves, light. That's kind of a big deal. I mean, it's essentially the Schrodinger equation is kind of like a wave equation. So it comes up a lot of places. Let's just get right to it and derive this thing. Like I said, I'm going to do it two ways. I'm going to do it a kind of non-traditional way first that I like, and then I'll do it a more traditional way. Okay, so we need to make some assumptions here. The first thing is that if you think about different parts of the string, they can only move up and down. So if I call this the x direction, they only move perpendicular to that. So they don't make these weird waves. Real strings do that, but we're not dealing with a real string. Okay, so there's that. Next, the deviations in the displacement are small. Okay, that is going to be important. So if you think about your string this way, we're not doing giant waves, just tiny, tiny little waves. Okay. The tension is constant. That one's not too hard to imagine. Everywhere on the string, the tension's the same. There's no gravitational force. The video I showed was actually on a flat surface. We're not going to worry about the gravitational force. We can probably add that later, but we're just doing a simple derivation. There's no frictional forces. You know, in my wave too, the beads rubbed on the table and there was a frictional force. No frictional forces. And then we're going to use a string of mass L and a mass M and a length L. Okay, so let's start. Here's our string. Here's a wave on a string. I just drew a string. And the first thing we're going to do is to break this into finite elements like that. So instead of having a continuous string with mass continuous distributed over the whole thing, we have just these pieces, and they're connected by no mass strings. Okay, and so we're going to separate them equally spaced this way. Remember, since they can only move up and down, if I equally space them this way, the distance between them might not be exactly the same, but the horizontal distance is, and we'll actually see that the distance is pretty much the same. And so they're all a distance delta x apart from each other. And then I'm going to number them just like a computer would, because this leads into the numerical calculation of the finite difference method, which I'm not going to do here. But that first one would be 0, 1, 2, 3, 4, 5, 6. And then they would all have x coordinates, x0, x1, x2, x3, so forth. And they would all have y coordinates. I stopped putting them on 4 and 5 and 6 because I don't really care. Then the mass of each of these pieces, if I have the total string has a mass of m and a length L, then the mass of each piece, I'll call delta m, is just going to be the ratio of the total mass to the length of that one piece. And so, yeah, right here you can see that, oh, this piece has a length from essentially here to there, right? So each piece is responsible for a length of delta x. So I get delta x over L is the ratio of the total length times the total mass. And I can write that as m over L times delta x, and I can call m over L the linear mass density. So not the volume mass density, the linear, and we use the Greek symbol mu to represent the linear mass density. And so that's a constant. So the mass of each piece depends on its length delta x times the linear mass density. Okay. Oh, and so then this is just to show you they can only move up and down. Each piece can only move up and down. That was one of the rules. Okay, so let's look at just three of these pieces. In fact, I'm going to look at piece number 2 here. And I want to model the motion or get an equation of motion for piece number 2. So there's two forces on piece 2. There's first this tension pulling to the left. I'm going to call it T1 because it's pointing towards piece 1. And then I have a force on this side, a tension I'll call T3 because it's pointing towards T3. And if I take the sum of these forces in the y direction, since it can only move in the y direction, the sum of the forces in the y direction, the y components of those forces, has to be the mass times acceleration. The mass is delta m, so this is the acceleration of piece 2. And that's just going to be the y component of T1 plus the y component of T3, and that's my Newton's second law. Now, we need to find the components of these forces. So let's think about T3. I want to use T3 as an example. And if it's pointing towards mass 3, which it's not a perfect drawing, but I think it works out okay, then the components of it are proportional to the distance components, right? So there's my triangle between 2 and 3, the distance triangle. So there's delta y, delta x, and let's call the distance between them s. Then I have my tension here. I drew it bigger so we could see it better. I have the y component and the x component, and those are similar triangles. That's really important, similar triangles, so that I can say delta y over the length, right? This ratio of the hypotenuse of the opposite side of the hypotenuse for this has to be the same for this one. So it has to be delta y over s is the same as T3y over T3. Now, T3, remember, the tension's constant. So the magnitude of this and the magnitude of this, magnitude of T1 and the magnitude of T2, I thought I put that somewhere, is the same. And we also have to say that if, I know I put T1 is equal to T2 somewhere. Okay, well, it doesn't really matter. I'd put it thinking later. If it's a super small deviation, if delta y is super small, then the length over here, delta x, is approximately equal to s. So s is equal to delta x, so I can write that as t. If I solve this for T3y, I get t times delta y over delta x, and that's what I get right there. Now, delta y is y3 minus y2. Right, that's just the change in y. And then delta x is just delta x. Doesn't really matter, it doesn't change. I can do the same thing for T1, but now there is a little bit difference, right? Instead of doing y2 minus y1, it's y1 minus y2 because it's pointing that way. Well, actually, in your video, it's pointing that way. Yeah, I always get this camera thing backwards. So because it's pointing in the opposite direction, the final piece, if you think about final minus initial, the final is y1 and the initial is y2. Okay, because it's going that way. So now I have T3y and T3 and T1y. I can find the total y force. I just add these two together. Now you'll notice I can factor out a t, I can factor out a delta x, and I get this. So F net y is, this is an important thing right here. I have positive y1, I have a positive y3, so I have y1 plus y3. And then they both have negative y2, so I get negative 2 y2 over delta x. So that's my force on one piece, okay, as a finite element. And it's important, so I put it in a box. I put things that are important in boxes. So let's look at that force. So here's that same exact equation. And if I want to, I could generalize that to the ith component. So let's just look at not item number 2. It could be any one, and I'm going to call it I. And so I can rewrite that as this is the force on I. This is the force on 2 up here, and so I have y2. So the force on I, I'll have yi. And then this is the number after it, so that would be I plus 1. And this is the number before it, so I minus 1. So I have t yi minus 1, the one before it, plus yi plus 1, the one after it, minus 2 of that actual element divided by delta x. And this is going to be equal to, that's the net force, so that's the mass times acceleration. And the mass is delta m, which I can write as mu delta x. And the acceleration is the second partial, it's the second derivative of y with respect to time, right? So I'm going to write these as partials because we're dealing with it just moving up and down. We don't have to worry about how it moves side to side. And so it's written as a partial derivative. Okay, so now I can do a little manipulation. I can divide both sides by delta x, and I can divide both sides by t. So over here, I get 1 over delta x. I get all that stuff. I can combine these two terms together. And over here, I get mu over t, second partial of y with respect to t. Now, I really want to just focus on this piece right here. If I bring the delta x in, I want to focus on just this piece. And I want to show you that this is the second derivative, the second partial of y with respect to x. I'm going to show you that. Okay, so here is how I'm going to show that. So this is just true in general, and this is the key to the finite difference method. So here are my 3 elements, and it doesn't really matter what they are. I have I plus 1, and I minus 1. And I want to focus on the first derivative at these halfway points, right? And you can do it different ways, but I'm going to use these halfway points. I want to find the slope right here and the slope right there. So I could call this this is going to be I plus 1/2. I know that seems silly, but it will make sense in the end. So this is the slope at I plus 1/2. Well, how do I find that? I could just take the change in y, right? That's going to be I plus 1 minus yi divided by the change in x, which is this delta x. So the slope is going to be at the 1/2 point is yi plus 1 minus yi over delta x. And then I can do the same thing over here for this slope. So this is the I minus 1/2. It's the point halfway over there. And it's just going to be final minus initial. So the final is going to be yi minus initial of yi minus 1 over delta x. So those are my 2 slopes at the halfway points. Now, I want those if I represent those as slopes right there at the halfway points, the second derivative is going to be the slope of the slope, right? It's going to be the rate of change, the space rate change of the slope. So I can take the difference in slope here and the difference in slope here to find the second derivative. So the second partial derivative of yi is going to be the change in, I'm going to say change in m, right? So I can do mi plus, it's actually I minus 1/2 to I plus 1/2. So it's just going to be the change in slopes divided by the distance, delta x. And I know those mi plus 1/2 and mi minus 1/2, right? So I just put in, this is just this right there. This is just this right there, divided by delta x. And they both have the delta x, so that becomes delta x squared on the bottom. Notice right here I have y plus 1, and then I have minus y minus a minus yi minus 1. And then I have minus yi, and I have another minus yi. So I get, boom, I minus 1 plus yi plus 1 minus 2yi over delta x squared. And that is your second partial derivative. So that's true for any time you break these things into finite elements. So there I showed that. Okay, so here we have, this is the second partial derivative. I just showed that. And we already said that's equal to the mass times acceleration, and we can divide both sides to get this. And that is your wave equation. And so normally we write this as T over mu on this side. T is the tension, mu is the linear mass density, second partial of y with respect to x. And so you see, the thing is, I went from finite to derive it. I went from finite elements to derive it. But then I showed that it doesn't really matter. That's the same as the second partial derivative. And that's going to be equal to the second partial derivative with respect to time. And that is your wave equation. Now, a lot of times we write it like this, so that we say the second partial of y with respect to time is equal to the velocity squared times the second partial of y with respect to position. And the velocity would just be the square root of tension over mu. Now, you can actually do this in more than one dimension. You could do this for a vector field. So you could do, say, it could be an electric field that comes up, or it could be really anything. And so F could be a vector, and then we get, this is the multi-dimensional wave equation. This would be a 3-dimensional wave equation. And so this symbol, some people call it different things. I like to call it I call it del squared. So that is in Cartesian coordinates. It's just the second partial with all these things added up together. So if you act that on this, you do get still a vector. So this is a vector side on this side and a vector on that side, and that's still the velocity. So that works. Okay, so that's my first derivation of the wave equation. Now we're going to do version number 2. This is one that's more common in the books, but I like this other one better. It just seems to make more sense. Fewer tricks, right? All these things have tricks in them. And I feel like that one doesn't have as many tricks. So here's our mass on a string. And I'm going to look at a part of it. I'm not going to break it into pieces. I am going to break it into pieces. But this is just a differential piece. And so this has 2 forces acting on it. Tension pulling to the left, tension pulling to the right. I call it T1 and T2. Now, I kind of drew T1 in a weird way. It probably should be in the direction of the string. But the difference in those is important. And I wanted to emphasize the difference in those tensions. So then the length of the string goes from x to x plus dx. And then I have these two horizontal lines, and I can measure the two angles of these forces T1 and T2. So here T1 is an angle measured from the positive x-axis to this point. But remember, T1 is pointing in the opposite direction. And then this is measured from the positive axis to that. It could be a negative number. It doesn't really matter. Okay, but that's important over here, again, because that one's pointing to the left. I have to measure theta in a different way. And then here's the thing I was thinking about before. So the magnitude of the tensions is the same. The magnitude T1, magnitude T2 is equal to T. So we could write down the Newton's second law for the x direction, and it'd look like this, right? So the net force in the x direction is going to be the x component of this plus the x component of that, even though that one's in the negative x direction. So negative t cosine theta, and this is going to be t cosine theta plus d theta. But if t is constant and theta is small, we already said that, then this is going to be just the same value. So the net force in the x direction 0, which we required, right? Because the mass can only move up and down. So if there's a net force in the x direction, it wouldn't move just up and down. So if we write the y equation, it looks like this. Okay, so here we have this force is T1. So I have because I'm measuring this angle from here, I have to include a negative sign, right? Because the force is pulling to the left. And it doesn't matter whether it's pushing up or down, there's still going to be a negative sign. Theta can be positive or negative. It doesn't matter. So that's my force for that one. That's the y component of that. The y component of this one is just going to be the same thing, but I'm using theta plus d theta instead. So I probably should put this before. So cosine theta is approximately equal to theta plus cosine of theta plus d theta, and it's approximately to 1, right? Because if you think about the cosine is the length of this. If theta is small, then the length of this is approximately equal to the length of that. So it'd be 1. Okay. I don't really like that either. Don't worry, you don't have to like that. Okay. I'm just doing what everyone else does. I'm a follower sometimes, not just a leader. Mostly a follower. Okay, ooh, that came down. I messed that up. You'll be okay with it. Okay, so here's that F net in the y direction equation. So I can factor out the t, so I get sine of theta plus d theta minus sine of theta. And then I can use this angle addition formula. So sine of a plus b is sine of a cosine of b plus cosine of a sine of b. I went through this. I'm kind of disappointed that it's in there, but that's fine. So let's go back over this. I should have drawn a triangle here, but cosine theta is approximately 1. We're talking about small theta. That was one of those important points at the beginning. Theta is small. So cosine of theta is approximately 1. D theta is even smaller, so it's definitely going to be 1. Sine of theta is approximately equal to theta, right? If you have a very, very small angle, then you're looking at that part where the sine function looks linear. And then sine of d theta, also if d theta is even smaller, it's definitely going to just be d theta. So I can write this equation for right here. I have sine of theta plus d theta. That's like a and b. So I have sine of theta cosine d theta plus cosine theta sine of d theta, and then I have that minus sine theta. And we can simplify this. So the first thing I can just say cosine d theta is 1. Theta is small, cosine d theta is 1. That cosine theta is also 1. And then I have, this is just sine theta times 1, so it's just sine theta. And then I have a negative sine theta. Those cancel. And then finally, I have this just sine d theta. I can just write that as d theta. And I know this seems like a stretch. It's like, wow, this is way too much. That's way too much, and it's not cool. But it is what it is. So I get the following equation, which I added over here already. So the net force is just going to be t d theta. Remember, factored out the t. This is just going to be d theta. And that's going to be dm, the mass of the piece, which is mu dx. Same idea before, I didn't show that. Times acceleration, and the acceleration is the second partial of y with respect to t. So that's what I have so far. Okay. So now we need to do another trick. This is a classic, it's a classic physics trick. And say, I can take d theta, and I can write it as the partial of theta with respect to x times dx. And it's like, oh, well, these dx's and they cancel. And, you know, some people say that's totally bogus, you can't do that. But if it was a finite thing, if there were finite delta x's, they would definitely cancel. So I'm cool with this, okay? Now, if we look at this triangle with a small d theta in there, then this would be dx, that would be dy, and this would be ds. And again, if d theta is small, then ds is approximately equal to dx, right? So sine of d theta is going to be ds. Sine is opposite over hypotenuse, so it's actually going to be dy over ds. But ds and dx are about the same thing, so it's going to be dy over ds, and which is just dy over dx. So this d theta over here, this d theta right here, this one is dy dx. Yeah. I know, I don't like this one either. So here I have t d theta, that's what I had before, is going to be equal to, then I put in partial of theta with respect to x, but instead of, oh, this should be theta? Partial of theta. I put d theta. This should just be d theta, partial, not, well, I'm going to keep going on. I don't like this derivation either. So I'm going to put in theta as dy dx. I guess you could do that if theta is small. That could be true. So I have partial of the partial dy dx over dx. This whole thing just becomes the second partial of y with respect to x. But I still have a dx term over there. So I have t second partial of y with respect to x dx. And then I just put that equal to the other side, mu dx, right? That's my mass. Second partial of y with respect to time, that's the acceleration. And then my dx's cancel. And then I get this. So there's my t over mu, second partial of y with respect to x, partial of y with respect, second partial of y with respect to t. And that's your wave equation. Whew, that one's tough. Okay. Now, let's go over a sample solution, because there's a lot of ways to solve this equation that can get kind of complicated. But I want to show you a solution. I don't want to solve it. I want to show you something that is a solution. So here's my sample solution to this wave equation, and then we're gonna animate it. It's gonna be fun, because you got to end with something fun, right? You get through that thing with that partial derivative, and I'm like, I'm not sure that's right, so we're gonna do something fun. So here's my solution. I'm going to show that this is a solution to this. So here's my function of x and t, right? So meaning if I move along the x-axis, things change, the y value changes, and if I move in time, things change. So I have a cosine kx minus omega t. Let's show that this is indeed a solution. So the first thing I'm going to do is to take the partial of this with respect to time, right? I need to take the second partial. I need to show both sides of this equation are true. So I'm going to take the partial of this with respect to time twice. I'm going to take the second partial and do the space. So here, if I take the partial of this with respect to time, I have the partial of cosine is going to be negative sine. And then I have to take the partial of the inside with respect to time. So I have negative omega. So I have negative a omega sine k x minus omega t. Now I need to take the derivative again. And now the derivative of sine is cosine. And then the derivative of the inside is going to be negative omega. So I'm going to get another negative and I get omega. So I have negative a omega squared cosine kx minus omega t. That's that. Now let's do the space part. So if I take the derivative of this with respect to space, I get negative a sine kx minus omega t. But then I have to take the derivative of the inside to get k. So I have a negative a k sine kx minus omega t. Take the derivative again, and I get the derivative of sine is cosine. I don't get another negative. I had it before. I get a k squared cosine kx omega t. Now, so here's my left-hand side, negative a omega squared kx minus omega t. And here's my right-hand side. I have the v squared, right? Don't forget the v squared, negative a k squared cosine kx minus omega t. Woo! Okay, so these a's cancel, the negative a's cancel, and the cosine terms cancel. So I am left with this. V squared would have to be omega squared over k squared. So if that's true, if we talk about the velocity of a wave, we're going to say the velocity is the wavelength times the frequency. I'm doing this in a roundabout way. Okay. We can define k as the wave number. K is the wave number. It's 2 pi over the wavelength. And the angular frequency is 2 pi times the frequency. So v squared would just be equal to this squared. So I put in lambda. No, I'm putting in this. Omega is going to be 2 pi f. And then k is 2 pi over lambda. So I get this. The 2 pi's cancel. And I get that is indeed true. So that is my wave speed velocity in terms of omega and k. Okay, so that solution did work. Let's make an animation. So I'm going to be using Web vPython, and actually I'm going to be using Trinket.io, and I will give you the code in order to make an animation that we need some values. So I just picked some values. I picked a string of length 1 meter and a mass of 0.5 kilograms, just so it looked fine. That's kind of too high, but whatever. And then the tension in the string, I imagine that I hang 50 grams over the end, so it's 0.05 times 9.8. That's the tension. And then the source, I can get the amplitude of the source and the frequency of the source. Again, I just picked some values. So I put 0.1 meter for the amplitude, which is kind of big, but it doesn't really matter. And 44 radians per second for the frequency, the angular frequency. Now for lambda and k, I need to calculate that. I can calculate lambda based on the k, right? And I can get k. So I did that already. How do you calculate lambda? Well, I guess I calculate v, right? I calculate the velocity based on the tension and the linear mass density, and then I can use that and the angular frequency to find the wavelength. And so this is the first part of the Python program. I cut off the calculations up here, but I'm going to break this into small time steps and small space steps. So I have t is 0, dt is 0.01, x is 0, and dx is 0.001. And then just to make things easier, I defined a function to calculate the y value. So it just returns a cosine k x minus omega t. That's it. And then all I do is go on, make a loop and move forward a tiny step in x and plot the position of the y value. Now, and this is what it looks like. But this is for t equals 0. So this is a snapshot. It's not an animation, right? But it's important to start with something that you feel comfortable with before moving on to things that are more complicated. So this does indeed work. So there's my animation. That's not my animation. That's just a snapshot t equals 0. Now I need to animate it. So in Python, and I'm going to give you the code to this. In Python, all I did here was I put a loop inside of a loop. So here's that same loop to calculate the value based on the position. And I do that loop for a whole bunch of different times, right? So I'm going from t is 0 to 5 and x from 0 to 2. So at the beginning of each time loop, I need to go back to the beginning and set x equal to 0. And then I do the same calculation, except I don't plot it. So one of the tricks here is to do this, you can call it whatever you want, but it's an empty list of the values that you want to plot. And this is how you do it in Web vPython. Other Python plotting packages do it differently. I like Web vPython because it's on the web and it works really well. So what you do is you empty the list, and then I add the data points to the list. And then when I'm done doing all that for all my x values, then I graph it. And that's what this line 32 does right here. It graphs it. And then I increase time, and I go back up here. Rate 1000 just tells you how fast to do these loops. This says don't do more than 1,000 of these every second. Since dt is 0.001, this will be in real time. Okay, so here's what I get. There's my animated wave on a string. There's the code up there. I'll put that in the link down below. So that's that. The wave equation, the derivation of the wave equation. I actually have a finite difference, a video on the finite difference method of taking any initial position of a wave with 2 fixed endpoints and modeling it. That's pretty cool. I think I might remake that video, but there you go. Derivation of the wave equation. Hope you like that. It's important. Okay, that's it.